Good morning, everyone. My name's John Leonard from MIT, and when I agreed to give a talk for this, I was going to be a skeptic, right? So are the skeptics right? But even in just the last sort of 5 months, they say there's sort of 3 phases to deep learning for vision researchers. Of sort of disbelief and denial, and then acceptance. And I was going to make a talk called skeptic, believer, or cautious user. And I was sort of migrating towards a cautious user. But then I got to know Larry Jackel, who was actually one of the first people to attempt deep learning back with Jan LeCun at AT&T at Bell Labs. I believe Larry actually hired Jan LeCun and is one of the co-authors on the first patent on using a convolutional network for digit recognition. And Larry released this video that just sort of blew me away a couple months ago from nVidia. And so I'm still wrestling with what it all means, but I really thought it would be better to hear from Larry, and because this is right at the cutting edge, but also a lot of decades of great history. So time permitting, I might come back at the end with my own sort of questions and thoughts, but I want to give most of the time really to Larry, so please.
Thanks, John. It says North Sea Technology. Actually, I'm a consultant to nVidia and also to Toyota Research Institute. But the work I'll be talking about today was done in conjunction with nVidia. And a little bit hard to see in this, there's a paper on arXiv, which is called End-to-End Learning for Self-Driving Cars. And the material I'm speaking about today is drawn from that paper. And I want to start out here. This is a short video of the self-driving car going on to exit 114 of the Garden State Parkway in New Jersey. Whoops, let's go back here. So that's Urs Muller, who leads the nVidia team on the left, and Jan LeCun is taking a video with his cell phone on the right. So we're going through the toll booth. The car's driving itself. I was in the back seat. I wasn't sure it would make it through the toll booth, but it did. Now it makes the turn. And it's being driven by a single camera, and you'll see that later on. But I wanted to give you a little bit of history and how we got to today, and start out with this. We had a machine learning group at Bell Labs in Homedale, New Jersey. And let's see, this is a pointer? Let's have to find out where to press. Where is the green button? There is no green button. Oh, that button, okay. All right, so this is the building we had in Homedale. We're actually working in that building now, and this oval loop here is our initial test track, and then we also can go out onto the local roads from here or from the entrance here. We were located in this part of the building. The building's about the size of the Empire State Building, but laying on its side. There are about 300 people in research, and we had about 30 people in machine learning. So the early results was in microfabrication. We were making recurrent neural nets following advice of John Hopfield. We made very small memories, very high density, took months to make, and they were basically useless. You could make one circuit to do some recall. But nevertheless, there was lots of hype, just as we have hype today. This was a cover of Fortune magazine from 1986. We had lots of coverage in the press, minimal science, no practical results. And I spoke to the guys from Fortune and sort of tried to play down everything and be really cautious and say we're just starting. And what they wrote there was Bell Labs breakthrough, chips that work like the brain. That was 1986, so that was, what, 30 years ago? Okay. All right. First applications, though, we were trying to make things useful. Hans-Peter Graf in our group, who's now at NEC, built a 54 neural chip that was programmable, which basically did analog summing, and the image of the chip's up there on the upper right. And I sort of programmed that thing to do feature extraction by hand, using essentially Yubel and Weasel-like features. And it was essentially a CovNet. We didn't call it that in those days, but there was no learning. And then Jan LeCun joined our group in 1988, and he built Lynette, which was a name we were playing on his name, so we called it Lynette, to do optical character recognition, OCR. And the big innovation there was having learned features, and the early benchmarks indicated excellent performance. And just, I don't know how many folks are familiar with this, but just to give you an idea of how these things work. Is this thing focused? It looks like it's not focused. Is there any way to focus the projector? Looks good, all right. So imagine that you have an image of some sort, and then you have feature extractors, which are basically convolutional kernels, and this cartoon is showing it pulling out horizontal features here, or maybe diagonal features here, and then you do a nonlinearity, and then you go and you look at various combinations of features, and you get more high-level features. Eventually, you get very abstract features, and you can do a recognition. So this is how CogNets were first used, and they're used essentially the same way today. We had great results. This led to first the NIST database, which led to MNIST, but we had no idea why this really worked. But then Vladimir Vapnik joined our group, and he gave us a much better theoretical understanding of how the process works. And by the early 1990s, we had a product at AT&T. We had applications in pen computing, finance, network fault prediction, and during this time, Vladimir, along with Bernhard Boser and Isabel Guillen, invented SVMs, and Karina Cortez did soft margin. We also got a write-up in the New York Times, and this time we're talking about working with the post office, and things were going great guns. The way that Vladimir helped us was to use two basic principles. One was something he called structural risk minimization, which means choosing the right structure of the network to solve the problem at hand. And that's really bringing prior knowledge into the learning machine. And why that's important is because it means that if you just go ahead and take a neural net package on the net and use that, you're probably not going to get great results. You have to find some way to structure the network that captures some essence of the problem. And that will give you much, much better performance. The other key idea is capacity control, and that's matching the learning machine capacity to the available data. And to do that, one examines the learning curves. And I don't think I have time to go into the learning curve stuff, but maybe later on we can talk about what these curves mean. But this is basically how one can determine how well a network will work depending upon the amount of training data that one has. Okay, so now, moving forward, let's go ahead 25 years to autonomous driving. So the usual approach people take for robotic navigation is the following. First, one has sensors, then we do feature extraction, followed by some kind of object recognition from which we generate a cost map. We do path planning, and then some kind of actuation like driving or the gas pedal. So what's happened most recently is people have combined the feature extraction with the object recognition, basically using the CogNets that I spoke about for the character recognition. And this certainly works, but at nVidia, we went one step further. We basically went and did the whole shoot and match from sensors to actuation. And the nice thing about it is that there's minimal use of handcrafted rules, which tend to be brittle, and minimal need for hand labeling. We don't have to have 600 people labeling all the data. So here's the training method. Human drives the vehicle, and we record what the human does, which would be the steering and the speed. And we also look at the imagery that comes to that. So we get training pairs. We have the image of the road, and we have what the driver does. Then we train a deep net to map the sensor data to the actuator commands, mimicking human. And then we evaluate the network in simulation and then on the road. So first attempt at things like this was done by Dean Parmelau at CMU in the early 90s. And he had low-resolution images and fully connected nets. He was limited by the compute power in those days. There was a seeding program at DARPA that Urs Moeller and Jan LeCun did in 2003 with higher resolution images and better compute power using CogNets. And this is the video of that. Let's see if this plays here. So this is in a junk pile behind one of the people's houses, and this robot on the left had to drive through this junk pile, and all it had was commands of somebody else in a different location steering the robot around, and it's trying to mimic that from the imagery. It had two cameras, but it wasn't told to use stereo explicitly. It had to derive that. So this looks quite promising, but basically the idea sat in the shelf for about 10 years, where this video was shown to Jensen Huang at nVidia, who got really excited and asked Ernst Miller to try and update the technology for use in self-driving. So with that, we did a fairly large CovNet, and this is the architecture that, I don't think you could read the lettering in your seat, but you can find this in the archive paper. There were about 250,000 distinct weights and about 27 million connections in this network. And the data collection for it works in the following way. The human drives the car. We pass it through an NVIDIA Drive PX box and record that on a solid-state drive. Also, we have a left camera on the windshield, the center camera, and a right camera. So we're recording three different views, slightly displaced. And then what we can do is we can augment our training set. We first have these pairs of the view from the camera and the driving commands, but we also can go and get all the spaces in between. The problem is that when you drive, you can't do stupid things. You can't drive way off to the right. You can't cross the line. But we can do that by shifting the images around. So we can take an image like this one, and then we can find the horizon, and then shift it over. So here you're driving on the left side. Here you shift it over toward the right side. You get some artifacts. You see the trees bend a little bit here, but it turns out not to be a problem. Then for training a network, we start out, we have the three cameras. We introduce a random shift and rotation. We pick the camera which gives us the most appropriate shift of the three that we recorded. And we also pass in the steering command from the human driver. And then we pass the imagery into a convolutional net, and that puts out a steering command. We compare that steering command to the command from the human driver, and we use backpropagation to reduce this disparity. So we did all this stuff initially in simulation, mostly last fall, and we tested it out on a Husky robot at 2 miles an hour, and then we got a drive-by-wire Lincoln, and 2 days after we got the Lincoln, we were driving on the highway outside the Bell Labs complex. So for this talk, I'm talking about what we did with 72 hours of training, mostly done in New Jersey. The weather was very varied, day and night, and we only used data when the driver stayed in the lane. But using this data, the car was able to drive at the nVidia headquarters in Santa Clara. I think I can say a few words about the simulator that we used. We record the video. We have a library here. We can shift and rotate it. And then we can simulate what the view would be like from the vehicle. We pass it through the convolutional net. We update the position, and then we shift and rotate again. So you can, using these very simple imagery from the initial driving, we can see how the car is going to drive as if it were driving in all directions perpendicular to the road direction. Okay, so here are some results. We have a metric we call autonomy, which is 100% times 1 minus number of interventions times 6 seconds divided by the elapsed time. The 6 seconds is the time we think that it takes for a driver to recognize a mistake and then correct. So, for example, if we have 10 interventions in 600 seconds, in other words, 10 minutes, the autonomy by this measure would be 90%. So using this metric, we found that on local and residential roads in New Jersey, we're at 98%. On the Garden State Parkway, which is like an interstate, we went 10 miles, no intervention, then we got bored and drove on home. Now, 98% is nice if you're doing character recognition. It's a complete disaster if you're trying to drive a car and not get killed. So we've got a ways to go, and we're well aware of that. Okay, so I wanted to show you a video now. Oops, not this one. I have a better version that I think plays better. You may want to turn the sound up for this. This is driving at the Bell Labs building, where nVidia now has a location in New Jersey. So the CovNets were actually invented in this building that we're using, and now it's driving the car.
Beautiful.
So the steering is controlled by the Drive PX. That's the this box here, and it sits in the trunk of the Lincoln. And there's an Omnivision camera. The lens is over here looking out. So one camera is all that's required to drive the car. It's 3 cameras for data collection, but just 1 to drive. So I've made this clip a lot shorter than it was. But this is the nVidia car. It's driving on Garden State Parkway. And drove for a while. We manually changed lanes, and now it's driving in the middle lane. It didn't seem to care much which lane you drove it in.
Let me put down my phone.
This is one of the roads right outside the Bell Labs complex.
Next time.
And good auto, 35 miles per hour. Oh, it's too fast. It's a little more exciting than yesterday.
Whoa, someone might fall out or...
So we had cell phones talking back and forth.
No, we're fine. We might fall out of the car though. We're going a bit fast.
What do you mean you're going too fast?
It's fine, don't worry.
It's the speed limit.
No, the speed limit's ridiculous. It's way too fast. So dangerous.
I have no idea what you're concerned about, Daniel.
Don't worry, he's just from Canada.
Okay, here comes the very sharp bend. Can you see it?
Yep.
It doesn't take it beautifully, but it always took it.
Takes it like a human.
That's not so bad.
So all those boxes on there are just junction boxes. There's no sensor. You can see the back of the car.
Yeah, it is actually open.
Yeah.
Look at that.
All right, we should go data collect there.
So we go 20, yeah, we should. So 20 miles per hour now.
Good?
Yeah.
Correct it. It took a little second to correct itself, but yeah.
I mean, we have room for improvement, but just a few days ago we wouldn't drive these curves at all. But this one is rather nice. Don't worry. And here we really
Notice there are no lane markers here at all.
By the way, we're going 14 miles an hour, just so you know.
14?
Yeah.
Yep, okay. It's like 6 meters per second, yeah. Okay. Oh, you're a little...
I think the wipers made a difference.
Actually, it moved away from the...
Yeah.
auto. Yeah, it's still totally autonomous. Okay, let's see if we can make the dirt road.
This is in a county park in Homedale. I was driving on dirt road. So I was standing there taking the picture, and I was pretty confident I wouldn't get run over.
You're brave, Larry.
I trust you. This is the same road. This is Urs Muller, not driving the car. He's deliberately looking bored. That's the camera that's driving the car. These are just some of the feature maps. This is what the network sees, and these are some of the feature maps that are being derived. You can see it's picking out the corners of the dirt road there. You can see that over here as well. The imagery was sometimes pretty crappy, but it still did a reasonable job. Here, this is the front of the building, and there was no road, just going through the parking lot, but it managed to follow the path and not hit any of the cars.
Look how well this car is driving itself.
That's Mario. She's very proud of his work.
Such a smoothness.
So here it's memorized going around a loop on that circumferential road. That's Urs. And this we set up in the parking lot. We had a film crew that tried to drive behind us. They couldn't drive as fast as this car. That's the same course. Now, I put a GoPro on the road there, so you can see what the car drive by the GoPro. Look at the hands sticking out of the roof here. So I think that's for this one. Yeah. So let me close this. Okay, so I want to just give you some conclusions. So the end-to-end learning shows a lot of promise for self-driving without explicit object recognition, path planning, or even detailed maps. But I don't think that the end-to-end learning is going to do the whole job. We need a mixed system that recognizes objects like traffic lights and stop signs. You could learn that by watching a driver try and stop in front of stop signs and traffic lights, but it would take much more data than we really would want to collect. And we really just scratched the surface using end-to-end learning. Thank you. Okay, it's probably my fault. What happened is that the stuff we did in 2003 was a seedling program at Arbor while I was a program manager, and we had that work done to convince the Arbor management to let us go ahead with learning how to drive. It was a logger program, learning applied to ground robots. And what I did in the program was to ask people to submit code from a standard vehicle every month or so that we could test. And they didn't have to submit it. They could wait a while or whatever. But they felt an incredible compulsion to submit every month. And rather than take a risk, they went and followed the usual path. And maybe Raya will address that because she was one of the performers in that program. So instead, people went and did pretty much the standard approach. And that worked reasonably well, but it sort of kept us at a certain level. And I have to give a lot of credit to Jensen Huang at nVidia, who when Urs showed him that video, he got really excited to do that.
I think I have 2 minutes or a minute.
You have more like 5.
So I really wanted to hear Larry speak and not me, and now you can see why. I think I'm just sort of blown away, not just by this work, by Mobileye and Tesla's progress. And I think if you could summarize sort of the last 10 years of driving research since the Urban Challenge in 2007, Google showed what you can do with really detailed prior maps, and just amazing levels of robustness in their home turf and Mountain View, and now in some new locations. But Tesla sort of came out of nowhere with the autopilot deployment, amazingly deploying the hardware a year before they activated the autopilot, but harvesting data from the fleet, and they've now said they were running code inertly in vehicles to test how it would work. And Sterling Anderson from Autopilot said recently at MIT that they've had 780 million miles of data collected from Autopilot users with 100 million, that's with just the sensors, but 100 million miles of Autopilot driving. So we live in an age where he or she who has the data wins, perhaps. It's just the opportunities by the computation and the data. But going back to Larry's presentation, there's a part of me that is just almost sad about this end-to-end thing. Like everything we've been working on, like thinking about data association and state estimates and covariances and having uncertainty bounds. I hope that all of the work we've done on probabilistic inference isn't just sort of thrown out the window. I think we need some sort of blending where deep learning gives us, in effect, I'm on board with deep learning as a sensor. There's something that can detect things with certain reliability and bounds. And I'll just be honest that I'm really torn over the end-to-end thing because I don't want to be a denier for what I see is tremendous progress. But it's pretty exciting times, and I think, ignore deep learning at your peril, perhaps unfortunately. So I guess it's time for the next speaker, so we'll stop there. But thanks again, Larry, for the
Just to echo something that John said, do we really think that hyperparametric function approximation, which is essentially what all these so-called deep techniques are, do we really think that that's going to solve the entire problem, every aspect of it? Do we really think that a hyperparametric function approximation is going to be the answer to the street signs that you pointed at and understanding what to do in response to a construction worker? Is this the only architecture that's going to get you all the way, or do you see actually places where something fundamentally different has to be incorporated?
Well, I don't think this is going to solve everything. I think if you had infinite amount of data, you could learn street signs and traffic lights, but why do that? I mean, if it's or traffic rules, there's a lot you just want to put in by hand or use other methods. So I imagine we'll have a hybrid system. I don't think end-to-end's going to do everything.
So can you say what that might look like? Maybe?
I think what you're going to see is that you'll have an output from the end-to-end system, and that's going to go into some kind of mediation box that looks at the environment and then makes a meta decision on top of what the end-to-end system shows you. But beyond that, I couldn't say. We haven't done it, so I can't really say. But you can imagine. I mean, I think it's probably going to be pretty straightforward engineering to do that.
Nick, do you reckon it's going to be, can we do end-to-end, trying to do everything?
So no, I actually think that's not true. And so your mediation box is interesting, Larry, because that can't be a deep system. It can't be a hyperparametric function approximator because it needs to reason about what it doesn't know. And that's exactly what deep learning and hyperparametric function approximation is terrible at. So I actually think that's an interesting idea, and you're pointing at something that absolutely cannot be a hyperparametric function approximator.
I couldn't say. I mean, I'm reluctant to. I imagine that we'll certainly have a hybrid system, but the details of that, I think it's kind of risky to make those prognostications now. You might be right. I couldn't say.